They're all a bunch of shortcuts.
Okay. Talking about conics today. And there are a group of, they are geometrical shapes that we will be covering 4 different ones. There are 4 different conics covering over the next few weeks. So we'll talk about what a conic is. We're going to focus on the circle today. We are going to do the parabola tomorrow, but we're going to do the parabola with different characteristics than an algebraic parabola has. So you'll see that it has full of other pieces of information that we look at, and not just a vertex or an axis of symmetry. So it does have some other information that we will be kind of focusing on to give it like a little bit of a geometrical aspect. So this is called analytical geometry. So kind of think that it is algebra based, and a lot of geometry is algebra based, but we will be analyzing some specific shapes, geometrical shapes that are created from a cone, which is why it kind of is based off of geometry. So a cone creates these shapes that we'll be looking at. They're not going to be functions, which is why they're not really algebraic per se. Algebra has functions, trigonometry has functions, geometry shapes are not functions. They don't pass the vertical line test, but they're still graphs, and I can still algebraically solve for them. So it kind of gets embedded into trig and pre-calc. Tonight's homework, you will be doing some graphing of circles, but also finding equations of circles, which is what we'll focus on today, and finding intercepts of circles. And a circle has 2 intercepts for x and 2 intercepts for y to cross through the y-axis twice since it's not a function as well. So if you can go to the chapter 9 packet, we're going to start looking at what these conics are and how they are created. Tomorrow, usually you guys have been lucky, like Wednesdays have been pretty laid back days in trig and pre-calc. Tomorrow we'll be doing a full period of notes, I hope. Not a laid back day tomorrow, but at least it's the parabola, which you know stuff about, you know information about a parabola. But like I'd say the last couple of Wednesdays in here have been pretty decent. Like it just ended up being review days on Wednesdays, and that was just pure luck. It's just the way the schedule kind of worked. Not tomorrow. Darn. You all say darn. All right. So section 9.1 has 2 different conics in it. And the first one we're going to look at today is the circle. But we're first going to define what a conic section is, and I will refer to this just as a conic. So you will hear me call it a conic and not a conic section. So a conic is the intersection of a plane, that's a geometry word, and double napped cone. Notice the word cone in the word conic. So a conic is created from a double napped cone and the intersection of a plane. So thinking back to geometry, a plane is a flat 2-dimensional surface. So think of a piece of paper as being a plane. When you graph the XY axis, you're graphing in the XY plane. So the XY coordinate system, or the XY plane, as we call it. So just really like a 2-dimensional piece of paper. A double napped cone, unfortunately, I only got one of these, and I'm the only one in the department that has it. So a double napped cone would be another cone, the tip of the 2 cones meeting at the point and it going in the opposite direction. So a circle is created when a plane intersects with a cone. And it's going to intersect, if the cone is vertical, the plane would intersect with it perpendicularly and go directly through my cone and slice through it, creating the circle. See, this is a cute little cone that I have here. So that's how a cone is created. So this cone or a circle is created. So my conic, my cone, and a plane slicing through it. Tomorrow, we'll look at a parabola. And a parabola exists, again, actually just from one cone. And it's slicing through kind of in like a diagonal form. And if I slice through diagonally, this one fell off. Then I have a parabola. My parabola could go left and right, depending on the direction of my cone, or it could go up or down. So we'll graph parabolas that could go left or right if my cone was facing in the left or right direction. So we'll have horizontal parabolas and also vertical parabolas, which we know in algebra, a horizontal parabola doesn't exist because it's not a function. So the other conics that we'll talk about also deal with slicing through a cone in a different diagonal format. We will look at something called an ellipse. It comes off, there we go. And an ellipse is kind of, think about it like an oval. You have an oval mirror. Oval shaped is what an ellipse is called. And that again is when it slices through the whole way through the cone, but more diagonally. And then the last one we'll do is a hyperbola. That's the only graph that needs two cones, or the only conic that needs two. So it would slice through vertically down one cone and through the next, and then it's going to have two parabolas facing in opposite directions. So those would be the four conics that we will talk about, and we will kind of look at them as we cover this conic group of geometry terms, really. So it is considered geometry because it's made from a cone, which is a geometrical shape, three-dimensional shape. So we'll talk about first the circle, and we're going to define it kind of using a geometric definition. And apparently Mr. Cummings was just talking about circles today as well. We'll obviously go in a little more detail with those circles because we're going to be algebraically trying to take an equation and get it into a circle form. So it does say underneath the conic section that we will approach conics by defining them as a locus. A locus is a collection of points satisfying a certain geometric property. So each one of these conic sections that we look at has a specific property that matches some type of geometric property. But it's going to start off with a collection of points or a set of points. So that means I have all of these points that are connecting together to make a specific geometrical figure. So a circle is the one we'll look at and define. A circle is a collection of points Let's do. That group of words is called a locus. I'm not going to use that word, but that is really what the term, that group of words, a collection of points, that is called a locus in geometry. So a collection of points that are equidistant. That means equal distance, but this is an actual geometric term. I'm not making this up and I'm not spelling it wrong. The same distance, so a collection of points that are equidistant from a fixed point. So the geometric property that they're meeting is that all of these points are the same distance or equidistant from a fixed point. And that fixed point is the center. Maybe we'll put that in parentheses. So a circle is created because we have a whole bunch of points and all those points are the same distance from the middle point. That's how a circle is created. So I can go any point at the edge of the circle and get to the middle. It should be the same space. Peter, how would you define a radius? Yeah, that sounds right. So the distance from the fixed point he said to one of the, we'll call them outer points, that's fine. So the radius we know has to go from the fixed point, which is really the center, to the edge of the circle. And then of course, the center is our fixed point. And our center is going to be represented by H and K. We use H and K graphically a lot in algebra. It represents the vertex of a parabola. It represents the turning point of an x cubed function. It's that middle point. It represents the starting point of a radical function. So H and K is also the vertex of an absolute value function. Most of the functions we've graphed have contained that H and K. Well, the conic sections that we will graph will also contain the H and the K. So a circle and all of the equations that we look at have a standard form. By understanding the standard form and the way it's written would actually determine the type of conic you have. So by the time we get to the end, you'll be able to look at the equation and say, this is a circle because it has this. This is a parabola because it has this in the equation. So a circle is the form x minus h quantity squared. H is your x of the center, so it's going to be with the x variable. Y minus k quantity squared, and that's equal to r squared. We talked about the unit circle in trigonometry. The unit circle in trigonometry was x squared plus y squared equals 1. When both your x and your y are squared, and there's being added together, that's a circle. The value on the other side, when I take the square root of it, represents the radius. So we worked with the circle a lot in trig, and that was the unit circle specifically because the radius was 1. So we're going to look at this first graph here, or this first problem, and we're going to start off basic and then of course work our way up a little bit. It says graph the equation by hand. The quantity x plus 3 squared plus the quantity y minus 2 squared is equal to 16. Determine the center and the radius of the circle. So in order to graph, you need to know the center and the radius of the circle. So look at the equation. From the equation, see if you can determine the center and the radius of the circle. And remember, the center is H and K. So kind of compare the equation to the standard form. And what do you think the center of the circle is?
Would it be or -3?
Yeah, why'd you correct yourself and say -3?
Because it's -h.
Yeah, so the equation is x minus h, and that's the standard form for any equation. It's x minus h. And then it's also y minus k. So this is really x minus a -3, which is why that h value is -3. Hannah, how about the radius? Excellent. And the radius would be 4. Because the r squared, 16, I need to take the square root of that. That 16 represents r squared. So when you go to graph this, I already knew I was going to graph, so I kind of pulled up the graph from the assignment posted, but you can just draw yourself a little XY axis and some tick marks. Doesn't have to be anything fancy. I do have graph paper posted so that you can use graph paper for the assignment. You're going to start first by graphing the radius at -3, 2. So again, you feel free to just draw an XY axis and place some tick marks. Or if you know you have a piece of graph paper somewhere saved on that iPad, you can go and steal it and paste it in. So we're going over -3 and up 2. And that would be our center. To graph a circle, it is the set of points that are the same distance from the center. So if I go from the center, Hannah said the radius is 4. If I move 4 points or a distance of 4 from the center, 1, 2, 3, 4, if I move to the right, I now have a point on the edge of the circle. I can move to the bottom and get a point on the edge of the circle. That is a distance of 4 from the center. I can do the same thing and move above, or I could do the same thing and move to the left. Now, you cannot move in the diagonal form because we know diagonally I cannot count 4 exact units. So go vertically and horizontally, and then connect your points with a circle. So we'll see how this looks once I connect them. Oh, not very good. Try again. My circle looks bad. This pointing a little more. Well, didn't want to connect good for me. That doesn't look too bad. I think I must have picked my pen up. Any questions graphing a circle? Start from the center, move 4 directions vertically, horizontally, not diagonally. So the second question wants us to use the standard form of the equation with a radius of 3 and the center of 1, -2. So write the standard form of the equation with a radius of 3 and a center of 1, -2. This is what you would have done in geometry. You would have been given the center, you would have been given the radius, and you would have been asked to write the standard form. So remember, x minus h quantity squared, y minus k quantity squared equals r squared. So Joe, what would that standard form of the equation look like if our radius is 3 and the center is 1, -2? Yep, that's it. So center is h and k. The radius is 3. When you plug it in, you square it to get 9. Questions? So we're going to now look at the more algebraic side of it. And the next couple examples, we will be doing a little more algebra work. The next example says the point 1, 4 is on a circle whose center is -2, -3. Again, write a standard form of the equation of the circle. So if our goal is to write the standard form, we want that x minus h squared, y minus k squared equals r squared. That's the standard form. So anytime you see standard form, my end result needs to look as a quantity of x squared, quantity of y squared equals r squared. The point 1, 4 is on a circle with a center of -2, -3. Find the standard form of the equation. How do you think you would approach this problem, Peter? We could use the distance formula, but we actually don't have to use the distance formula, but you could, because you could find, if you use the distance formula, what would you find? So that would be the radius. So you could use the distance formula to find the radius. Yes, that would work. What else could you do? Yeah, you could also plug in the point for x and y and the center for h and k. That will also find the radius for you. Either one, but the formula here is pretty much, Peter, if you look, it kind of is the distance formula. The x minus h squared plus y minus k squared, the distance formula would just be the square root of that, which is really what we're going to be doing. So either way, you're kind of finding the same information. Hi. Let's see if we can plug that in. I give you the money?
Yeah.
Yes.
It's $3.
Okay. There you go, sir. Thank you. I got the s'more cookies. I was disappointed the last time they didn't have s'mores. My kids were really disappointed too. So plug in 1 for -2, -3 for the X, the Y, the H, and the K. So X is 1, H is -2, but becomes a +2. Y is 4, K is -3, but becomes a +3, and then that's equal to R squared. So Parker, 1 and 2 squared becomes 4 and 3 squared. And add those together, you get, yeah. Now remember, the goal is to write the standard form of the equation. That is R squared. You don't need to take the square root of it because you want R squared for the equation. So our standard equation, plugging in just the center, would be X plus H, or X minus H, which is really a +2. Y minus K, well, that's a +3. And then it's equal to R squared, which Parker said was 58. Don't take the square root of it. Again, you want that R squared value. That's what you're solving for in the standard form. Yeah.
If you were trying to find R, you take the square root of it, you would have to be plus minus, right?
No, yes, technically, but because it's a radius, it's always a distance, it's always positive. Yeah. All right. So building on the algebra and the completing the square that we did yesterday. If you look at the next example, use completing the square to get this general form. So a general form is when your equation is expanded and it's equal to 0. Into standard form, identify the center and the radius. And I showed you this equation yesterday. So we have an expanded form of an equation. I have 2 squared terms, x and y. And then I'm adding 4x, subtracting 6y, and adding 12, and this is equal to 0. We're going to use completing the square to take this equation and to get it into standard form, which means that in standard form, we should have, come on, buddy, our x squared and our y squared and the r squared, that quantity squared. So think about completing the square and look at the equation that's given and what we're trying to get to. Darby, what do you think you could try and do first with this expanded general form? Yeah, let's get the 12 to the other side. The first step is to isolate C or to eliminate C. Well, in this case, that plus 12 is our C term. That's the constant. So we're going to take that to the other side. In the same step, Darby, what else do you think we could do to kind of like organize information? Yeah, so we're just going to kind of move things around so that your x terms are together and your y terms are together. So we have an x squared and a 4x. And then we have a y squared and a -6y. And that was equal to -12 because we took the 12 to the other side. You're going to complete the square, but you're completing the square for both x and y variables because our goal is to have a quantity squared for x and a quantity squared for y. So starting with the x, Jack, we have x squared plus 4x. We need to complete the square for the x. What would we do to complete the square? Yeah. So you're taking b divided by 2 and squaring it, so you're adding 4. Where else does that 4 go, Jack? On the other side. How about for the y's, Jack? That line also goes on the other side. So now you're adding 2 numbers to the left to complete the square for x and then complete the square for y. Those same two numbers get added to the right, because whatever you're adding to the left, you have to keep it equivalent and add it to the right. So you're taking negative b divided by 2 with the x terms, and then negative b divided by 2 with the y terms. So Jack, when you go to factor the x, what would it factor as?
X plus 2 squared.
And then the y. And on the other side, 1. This is now the standard form of our circle. We have x minus h quantity squared, y minus k quantity squared equals r squared. Questions? So cool. What is the center and the radius of this circle? And the radius is just 1. So I'm going to graph this because you will be asked to graph, and just to make sure you're okay graphing. So we are going to graph this. He said the center is at -2, so over 2, up 3. And then the radius is just 1. So 1 in every direction, left, right, up, down. There we go. Does anyone have questions? So see if you can take the next equation and think about what you're going to have to do to complete this square. So use completing the square to find the general form of this circle. I'm sorry, the standard form of this circle. Identify the center and the radius. So think about the steps that you need to do to complete the square. We have 3x squared plus 3y squared minus 6x plus 12y, and it's equal to 0. There is not a constant term that you have to take to the other side. All the terms have a variable with them, so they need to stay on the left. So the variables on the left, the numbers go on the right. Think about the one thing that you have to do with this. What's that one thing that you'll have to do to complete the square? And then what did you do first to complete the square?
I put the X's and Y's together, and then took out the 3.
Yeah, so take out a 3 from each. Remember, the coefficient in front of the squared term has to be 1. So we're going to take it out, but separately. So you're looking separately, trying to group the y's together, separately trying to group the x's together. So I'm individually taking that number out. So Evan, when you complete the square with the x's, what number would you add?
Plus 1 for that.
I didn't take it out right. Huh? Yeah. There we go. And then what number goes on the other side, or what numbers go on the other side? If you factored out a 3. Nice. So this becomes 3x minus 1 squared, 3y plus 4 squared, y plus 2 squared, is equal to 15. And then when you get rid of that 3, x minus 1 squared, y plus 2 squared is equal to 5. Questions? So Kaden, the center and radius. Right. So the radius is the square root of 5. It's okay for the radius not to be nice, perfect, exact. It's going to happen where the radius could be the square root of 5, a little more than 2. Still graphable. We'll definitely be graphing values that aren't quite exact. We'll just estimate. All right, so are there any questions on completing the square with the 2 variables? We will use completing the square for every single one of these problems. Yes.
Why is the radius square root of 5, but the one on the problem above it, which is, I'll wait. for the square root of 9.
Huh, look at that. Answered your own question as you were talking. Any other questions? All right, so the last one on here says for us to find the intercepts of the graph. Not only is it important to have a center and a radius, but the other important features of graphs are those x and y intercepts. So graphically, most functions, we find those important characteristics, whether it be the vertex and then the x and y intercepts, or the critical point and the x and y intercepts. But when you're graphing with x and y intercepts makes it a more precise graph. So we have this problem already in standard form. If it was in general form, so notice the difference between general versus standard. I call general the expanded form. Standard form is the quantity squared. That's easily graphed. So if an equation is given in general form, you'll complete the square to get it in standard form. But this equation is in standard form for us, and it wants us to find the x and the y intercepts of the graph. We're going to do this algebraically. How do you find an x-intercept? Or how do you find a y-intercept? Yeah, so if you're finding the x-intercept, Hannah, you set y equal to 0. And if we're finding the y-intercept, you set x equal to 0. You want it to be in standard form first, though, because I can solve this using the square root process that we did for finding or completing the square and solving for x. So in this problem, the x-intercept, she said let y equal 0. So x minus 2 squared, 0 minus 4 squared equals 16. Or 0 minus 2 squared, y minus 4 squared equals 16. So you're solving for either x or y, depending on the intercept you're finding, by letting the other variable be 0. So Gianna, how would you start solving for x for the x-intercept? So if this is 16, what happens when you take it to the other side? It would become 0. And then what would you do, Gianna? So that means it's only touching the x-axis at one point, just the ordered pair 2, 0. Remember, an intercept is an ordered pair. It's a point where the graph crosses or touches the x-axis. In this case, the bottom of the circle is going to touch the x-axis at that point, at 2, 0. It's not going to cross through it. Instead, it's just going to touch at that single point. If you do the same steps that she just did to solve for y, 2 squared is 4. So we would have y minus 4 squared equals, and if I subtract 4, I get 12. Brenna, to continue to solve, what would you do here? Now, Brenna, do you think I could just take the square root of 12 in the calculator and get a decimal there? Probably not, right? What would you do with the square root of 12? Yeah, 2 square root of 3 with that plus or minus in front. So then we have 4 plus or minus 2 square root of 3. Again, an intercept is an ordered pair. We plugged a 0 in for x, and then the y is 4 plus or minus 2 root 3. So that means it's touching the y-axis twice. 4 plus 2 square root of 3 and 4 minus 2 square root of 3. So one above and then one a little below that. We will be graphing these by using like estimation. So the square root of 12 is a little more than 3. So 4 plus a little more than 3, 4 minus a little more than 3 to get those y-intercepts. Are there any questions? Circles aren't too bad, but you probably didn't quite go involved. Like, I'm pretty sure Mr. Cummings probably wasn't quite as involved with these circles. I don't think you complete the square in geometry. I think you do that in algebra. I know you do it in algebra too, but pretty sure you learn it in algebra too. So the homework for this evening will be a couple of each type of example that we worked on. So you'll be getting them in standard form using completing the square. You'll be graphing them in standard form or writing them in standard form if you have a point and a center. And then tomorrow we will talk about the parabola and how the parabola changes based off of the geometrical definition and not the algebraic definition. So we'll switch just a little bit. Any questions? All right, so if you're at home, have a fantastic day. A few minutes to just sit and chill.